Okay, so here's the extra practice on integrated rate laws, question 9. In the equation above, molecular iodine dissociates to iodine atoms. This reaction occurs according to first order kinetics. Rate constant is. And then it says calculate the half-life of the reaction. So looking on your integrated rate laws sheet, half-life for a first order reaction is equal to the natural log of 2 divided by k, or 0.693 divided by k. It gives us k in the question. So I take the natural log of 2, divide it by k, and I get 2.56 seconds. Then in part B it says, if the reaction begins with 0.05, calculate the concentration of I2 after 5.12 seconds. So this time I need the rate law, integrated, first order, right here. I know k, I just calculated the half-life from k. I need t, and they just told me that it is 5.12 seconds. And I know the original amount, which they told me right here was 0.05 molar. And I'll be solving for this animal right here. So here's my integrated rate law equation. And then here's the numerical values put in. So here is the rate constant. Here's the rate constant that I used right up here, 0.271. They told me that right here. Here's my 5.12 seconds. And then here's my initial concentration, or original concentration right here, 0.05. Okay, solving this side of the equation, I get this for the natural log. I get this for those two numbers multiplied together. Notice a negative plus a negative will give me a more negative number. And so the natural log of I2 is equal to negative 4.358. And then on your calculator, you need to take and do the inverse natural logarithm, or the e to the x key. And so you end up with e to the negative 4.358. And you should end up with 0.01245 molar. And then check to make sure that it makes sense. So you started with 0.05. Did it go down? And yes, after 5 seconds it went down to 0.124 molar. So it made sense that it got less. Then the last problem on this page is the extra practice on ice tables. And so the extra practice on ice tables problem says calculate the equilibrium constant at this temperature, because it gives us a bunch of data for it. So the equilibrium constant would be products divided by reactants to the power of the coefficients. So we're given 0.5 molar of the NH3, 0.1 of the N2, and 0.1 of the hydrogen. Raise those to powers. Ends up being 2,500. Then in letter B it says new samples are put out, and we have different amounts, and it says calculate Q. So Q is the same equation right here, but it's not at equilibrium. And so putting these numbers in now, square, cube, division, this is what I get on the top, this is what I get on the bottom, I get 112. Then it says indicate the direction which the mixture must shift to achieve equilibrium. And so now you need to compare these two numbers. And remember, the way that I like to compare them is over 1, because you can say it's always products divided by reactants, products divided by reactants. So here's my products, reactants. Here's my products, reactants. What do I have to do? Because I want to get to this. I want to get to equilibrium. Well, this number obviously has to get a lot larger if it's going to be 2,500. And so the reaction must shift towards the products, or shift right, or more products must be produced.